Upcoming videos, we are going to talk a lot about factoring, which is exactly the opposite of distributing, or sometimes distributing is called expanding. But before we get into that, we want to say, when is factoring useful? It's easy when you're doing algebra to get so caught up into doing a process that you don't really think about why you would want to do it. So when is factoring useful? So I'm just going to give you a couple of cases. There may be a couple of more, but let me start with the following. If we look at the expression 2x plus 4 over 4, by factoring it, we would be able to simplify it. You can note, if you're looking at the numerator, if we rewrote it as 2 times the quantity of x plus 2, it would be equivalent, because if you distribute the 2 times the quantity x plus 2, you would get 2x plus 4 back again, and the denominator remains 4. Now when you look at both expressions, the one on the left, it's not very obvious how you could simplify that expression. But if you look at the one on the right, you realize that you have a factor of 2 in the numerator and 2 factors of 2 in the denominator, but you could reduce by dividing both numerator and denominator by 2, and so you could end up saying, this looks like it could be the x plus 2 over 2, which is clearly simpler. X plus 2 over 2 is clearly simpler than 2x plus 4 divided by 4. So we would rather express it that way. So if we look at its factored version, which was what we have in the middle here, it makes it apparent how we could simplify the fraction. So when we have algebraic fractions, we can use factoring to simplify them, just like you used to do when you had numeric fractions. For instance, if I had 8 over 12, I would recognize that both of them have a factor of 4, and if I divide both the numerator and denominator by 4, I would be down to 2/3. So you've done factoring before with fractions, just never with algebraic fractions. So let me give you one more example of factoring for with fractions. So let's write x squared plus 2x over 5x. And let me remind you, factoring is the reverse process of distributing or expanding. So I think it's pretty clear that if I wrote the numerator as x times the quantity x plus 2, you could distribute that and get back to what you started with in the numerator on the left of x squared plus 2x. The denominator just remains 5x. But now in its factored form, it looks like we could simplify it. We have a factor of x in the numerator, and we have a factor of x in the denominator. So in other words, we're going to multiply by x, but then turn around and divide by x. So we can divide those factors out, although we're going to put one caveat on that. We can say that the fraction that we started with would be equivalent, it's an algebraic fraction, but that would be equivalent to the quantity x plus 2 over 5. Which could also be written other ways, like 1/5 times x plus 2. So those are all equivalent to each other. Now there is one caveat here. In the beginning, if we started with the original statement and we substituted 0 into the sub x equals 0, we run into major difficulties, because we get 0 plus 2 times 0 over 5 times 0, which is 0 over 0. Whereas if we substitute 0 into the later expression, we would end up with 2/5. So if I go ahead and substitute 0 in, I would end up, after factoring out the x's, I would end up with 0 plus 2 over 5, which is 2 over 5, which is clearly not the same as 0 over 0. 0 over 0 is a complicated thing. It's completely undefined. So what we would have to do is say that the original expression simplifies to x plus 2 over 5 as long as x is not 0. So we have to put a qualifier on there. But we can see it is much simpler to talk about x plus 2 divided by 5 than the original expression. So one final example of where factoring is really nice is if we're working with something like this, an algebraic equation rather than an expression. X squared plus 3x plus 2 is 0. So we want to find the values of x that would make this true. If we were to rewrite this as x plus 1 times the quantity, the quantity x plus 1 times the quantity x plus 2 equals 0, becomes a much easier problem. You can quickly check for yourself that if you were to multiply the quantity x plus 1 times the quantity x plus 2, you'll end up with x squared plus 3x plus 2. But I'll leave that to you to find out. But now we're in a position where we can invoke a special rule of arithmetic, which is the zero product rule. Let me just write this over here, the zero product rule. If some number a times some number b equals 0, then we only have two choices. Either a equals 0 or b equals 0. So if we applied that to the problem at hand by rewriting our polynomial as the quantity x plus 1 times the quantity x plus 2, we can break this into two problems. X plus 1 must be 0. Notice it's the word or. X plus 2 must be 0. They can't both be 0 at the same time because of the numbers involved, but one or the other could be 0. And clearly, if x plus 1 equals 0, x would have to be negative 1. And if x plus 2 were to equal 0, x would have to be negative 2. So if I could figure out the factored form of x squared plus 3x plus 2, which we have done for you here, and written it as the quantity x plus 1 times the quantity x plus 2, it allows us to invoke the zero product rule. Now, the only reason we can use the zero product rule is because the whole thing is equal to 0. So when we rewrite this as one factor times a second factor equals 0, this rule can be invoked, and it makes solving the problem very easy.